Hello students, in this lecture we will talk about potentiometry. The lecture plan includes information on introduction, the electrode system used in potentiometry, indicator electrode, metal electrodes, ion selective electrodes, reference electrode, then potentiometric titrations, in which we will talk about acid base titrations, complexometric titrations, oxidation reduction titrations, precipitation titrations. Let us now come to the potentiometer. A potentiometer is a device which is used for measuring the potential of an electrochemical cell without drawing a current or altering the cell's composition. Potentiometric measurements are carried out using a device which is used for determining the potential difference between a working electrode, also known as an indicator electrode, and a reference electrode is known as potentiometric measurement. The direct measurement of an electrode potential from which the concentration of an active ion may be found and the changes in the electromotive force, that is EMF of a cell brought about by the titrant, is also known as potentiometric measurements. The quantitative relation of electromotive force of a cell is given by the expression E cell is equal to E reference plus E indicator plus E junction. Cathode is the working or indicator electrode, that is the right half cell. Anode is the counter or reference electrode, which is left half cell. The direct measurement of an electrode potential from which the concentration of an active ion may be found and the changes in the EMF of a cell brought about by the titrant. Now, again E cell is equal to E indicator plus E reference plus E junction, where E indicator is the potential of indicator electrode, E reference is the potential of reference electrode, and E junction is the liquid junction potential. The role of the counter electrode is reduced to that supplying a reference potential, and thus the counter electrode is called the reference electrode. Indicator electrode, that is the electrode that responds to analyte and donates or accepts electrons. Reference electrode is the second half cell at a constant potential. Cell voltage is the difference between the indicator electrode and reference electrode. Let us now come to electrode junction potential or junction electrode potential. Normally represented as EJ, is due to unequal migration of cations and anions at the boundary of a liquid junction, that is at a salt bridge interface. This charge separation results in a potential at steady state. EJ is minimized by a high concentration of a salt with nearly equal mobility of cation and anion in the salt bridge. For example, saturated KCl is used, in which the mobility of potassium and chloride ion is nearly equal. The flux of the migration of this electrolyte is much greater than more dilute ones and largely determines EJ. Let us now consider how we can represent liquid junction potential. Here we have a boundary, and one side we have 0.1 molar HCl, and on the other side we have dilute HCl, which is 0.01 molar. Now, in this case, at equilibrium we can see, say at plus 40 millivolt, all negative ions are accumulated on one side of the membrane and all positive ions they are collected on the other side of membrane. The use of electrodes to measure voltages that provide chemical information is known as potentiometry. Various electrodes have been designed to respond selectively to specific analytes. Two types of analysis are carried out by using potentiometry. First, the direct measurement of the electrode potential, from which activity or concentration of an active ion may be obtained. Second, to measure the changes in electromotive force brought about by the addition of a titrant to the sample. Electroactive species is defined as a species that can donate or accept the electrons at the electrode. Then let us come to potentiometric electrochemical cells. The electrochemical cell consists of two half cells, each containing an electrode immersed in a solution of ions whose activity determines the electrode's potential. For example, let us consider zinc and silver. When solid zinc plate is dipped in a zinc ion solution and similarly silver plate is dipped in silver ion solution, the reaction takes place ZnS, that is solid, plus 2 Ag in aqueous, giving 2 Ag solid plus zinc 2 plus aqueous. This can be represented in a better way by representing two beakers in which we have a solution of zinc chloride and in another one we have a solution of silver nitrate. In the solution of zinc chloride, a zinc plate is dipped, whereas in the solution of silver nitrate, a silver plate is dipped. Both are connected with a potentiometer and a salt bridge, which is KCl filled in a glass tube, is connected to provide a connection. At the end of these tubes, we have porous frets. Now, when we pass electric current, the zinc which is present in the plate is ionized to give Zn2 plus, and 2 electrons are evolved which travels through the wire to the potentiometer and comes to the cathode, where silver takes these electrons and gives silver ions in the solution. The activity of zinc ion in this case is 0.0167 molar, whereas for silver ions it is 0.100 molar. A salt bridge containing an inert electrolyte such as KCl connects the two half cells. The ends of the salt bridge are fixed with porous frets, as I told you, allowing the electrolyte's ions to move freely between the half cells and the salt bridge. This movement of ions in the salt bridge completes the electric circuit. Let us now come to the Nernst equation. Nernst's concept of electrode potential is, let us consider a species OX which is taking an electron to give reduced species which we are writing as RED. The electrode potential of this reaction is E is equal to E0 minus RT by NF log reduced species divided by oxidized species concentration, where E0 is known as standard potential for this redox couple, R is equal to gas constant, F Faraday constant, N number of electrons involved in the reduction, and let us now come to various types of electrode system. First class of electrodes are a metal in contact with the solution of its ions. The potential of the system in this case is represented by Em is equal to E naught plus 0.0591 by n log activity of Mn plus, where Mn plus is the metal having n positive charge. Second class of electrodes are metallic electrode, which are in contact with one of its very slightly soluble salts, may respond reversibly to changes in anion activity. For example, we have Hg mercury, Hg2Cl2 mercurous chloride and chloride ion. Similarly, silver, silver chloride and chloride ion. In this case, we can see Hg2Cl2 or AgCl are very slightly soluble salts. The potential of the silver-silver chloride electrode is represented as E is equal to E naught plus 0.0591 log A, that is activity of silver ions. We can also write it as E is equal to E 0 plus 0.0591 log KSP minus 0.0591 log activity of chloride ion. Third class of electrodes are a metal ion in contact with one of its own slightly soluble salts or slightly ionized complexes and with the slightly more soluble salt of a second metal or slightly more ionized complex of the second metal. The slightly soluble or slightly ionized compound must have a common ion like Ag, Ag2C2O4 or CaC2O4 and calcium ions. Similarly, mercury, Ag2C2O4 and CaC2O4 and calcium ions. Two broad classes of indicator electrodes are metal electrodes, that is for using or develop an electric potential in response to a redox reaction at the metal surface. Second, ion selective electrodes, which are selectively bind one type of ions to a membrane to generate an electric potential. Electrodes of the first kind, that is, an electrode of this type is a metal in contact with a solution containing its cation. The most common ones are silver chloride dipping in a solution of silver nitrate. Here, silver ions take an electron to give metallic silver. Similarly, copper electrode Cu2 plus takes 2 electron to give copper. Zinc electrode zinc 2 plus taking 2 electron to give zinc. The second kind of electrode or electrode of this kind is a metal wire that is coated with one of its salt precipitate. A common example is silver electrode and silver chloride as its salt precipitate. Then comes redox electrode, an inert electrode that serves as a source of sink for electrons for redox half reaction, or in another words, an inert metal is in contact with a solution containing the soluble oxidized and reduced forms of the redox half reaction. The inert metal is usually platinum. Inert metals, apart from platinum, we can also use gold, palladium and so on. These metal works as a good source of electron, or we can say they are electron source or sink. Redox of metal ion is evaluated and they may not be reversible. Then let us come to membrane indicator electrodes. In this case, usually non-crystalline membranes are used. For example, glass silicate glasses for H plus, Na plus, liquid ion exchanger which is used for calcium 2 plus, immobilized liquid PVC matrix for calcium and nitrate ions. Then we have crystalline membranes, single crystal lanthanum fluoride for fluorine, polycrystalline or mixed crystal silver sulphide for sulphide and silver ions. The properties of these electrodes are they have low solubility, solids, semi-solids and polymers. Some electrical conductivity often by doping can be achieved. Selectivity, they are part of membrane binds, reacts with analyte. Let us now come to types of ion selective electrode. Glass electrodes, solid state electrode, liquid membrane electrode, gas sensing electrode. Let us now come to a membrane electrode which is used widely for measuring pH. In this case, we can see we have a glass tube here at the bottom of which we have a glass membrane. Now, this is filled with silver chloride paste which is suspended between the sides of folded silver wire. The outside we have aqueous filling solution which is usually saturated with silver chloride and KCl. In the inner tube, the liquid level of inner reference electrode is present, whereas the liquid level of other reference electrode is filled outside. The air inlet is provided and these are leads to pH meter. The solution of analyte is taken in the beaker and the porous plug is to allow slow drainage of electrolyte out of electrode. In the glass membrane, just above the glass membrane, 0.1 molar HCl saturated with silver chloride is filled. The glass pH electrode has several advantages. Its potential is essentially not affected by the presence of oxidizing or reducing agents. It can work over a wide pH range. It responds fast and functions well in physiological systems. Let us consider a simple glass electrode. In this case, we can see we have a pH sensitive glass membrane at the bottom in which 0.1 molar KCl is filled. Now, we have a porous wake and the case was earlier. Here we have silver chloride reference in the outer side and silver chloride reference as internal electrode in the inside, and outside KCl solution is filled. Glass membrane pH electrodes are often available in a combination form that includes both the indicator electrode and the reference electrode. So, you can see here we have reference electrode present here and this is internal electrode or indicator electrode which is present in same electrode. Now, if we look for a solid state electrode, we see here we have a membrane at the bottom, internal solution of analyte, silver chloride reference electrode you can see here which are filled in plastic cylinder and the wire is going to the meter. A solid state ion selective electrode uses a membrane consisting of either a polycrystalline inorganic salt or a single crystal of an inorganic salt. The internal solution of analyte contains a fixed activity. Incorporated membrane is fabricated from insoluble crystalline materials and the material used are highly insoluble salts such as lanthanum fluoride, silver halide and sulphide, and thallium with metal sulphide. These types of membrane show a selective and Nernstian response to a solution containing either the cation or the anion of the salt used. It contains an internal reference electrode and an internal reference solution of fixed composition. A hydrophobic membrane containing a liquid organic complexing agent that reacts selectively with the analyte is present in liquid membrane electrode. Three types of organic complexing agents have been used, like cation exchangers, anion exchangers and neutral ionophores. Here, this is a simple representation of liquid membrane electrode. Here you can see this is a glass vessel at the bottom of which a membrane saturated with di-N-decyl phosphate is bound. The inner tube possesses a saturated solution of calcium ions, whereas the outer solution possesses di-N-decyl phosphate, and you can see the internal wire possesses a silver chloride reference electrode. Now, if we consider a gas sensing membrane electrode, it is slightly different. In this case, we have the outer surface, outer tube at the bottom of which a gas permeable membrane is fitted. The tube is filled with inner solution, whereas the second tube or the lower diameter tube possess silver chloride or reference electrode. We have now two electrode here, one the reference electrode and second internal electrode which goes to meter. The concentration of gas like carbon dioxide, ammonia, SO2, NO2 in aqueous solution can be measured with an electrode consisting of a glass electrode and reference electrode pair inside a plastic or glass tube. Now, the membrane consists of a microporous hydrophobic plastic film through which only gases can diffuse. No species in the solution can interfere with the electrode response because only gas can diffuse through the membrane. Any gas that can change pH in the internal electrolyte solution can affect the electrode response. If we consider advantages of the ion selective electrode, continuous monitoring of various components in flowing samples such as measurement of fluoride in water and calcium ion in biological fluids is possible. These electrodes are used in clinical analysis, pH, blood gases like oxygen, carbon dioxide, electrolytes, sodium, potassium, chloride, calcium, magnesium, lithium, and metabolites like glucose, urea, uric acid, lactate, and so on. Let us now consider reference electrode. The most essential properties of the reference electrode is that its potential remains constant throughout the course of a single titration. Here you can see we have a Hg2Cl2 which is saturated and KCl. This is saturated KCl or saturated calomel electrode. You can see here we have a fitted disc here and we have a small hole at the bottom and we have a inner tube containing a paste of Hg2Cl2 and saturated KCl. Then the electrical leads which provides connection are used for the purpose of connection. These are the reference electrode commonly used in potentiometry. The calomel electrode, if we consider in a little bit more detail, here mercury is in contact with its chloride. You can see here we have a porous wick, a hole, and in the porous wick we have KCl crystals, and the inner tube possess mercury, mercurous chloride and KCl, whereas the outer solution possess saturated KCl. For providing connection, we have mercury at the top of this paste, which goes to potentiometer. Similarly, silver chloride is also used, in which a silver wire is coated with the silver chloride either by electrolysis or by dipping into the molten salt. The wire is immersed into the filling having known concentration solution of KCl, generally 1 molar, saturated with silver chloride. Here you can see we have a porous plug, KCl solution, and this is silver wire which is coated with silver chloride at the bottom, and the connection goes to potentiometer. In potentiometric titrations, the change in the electrode potential upon the addition of the titrant are noted against the volume of the titrant added. At the end point, the rate of the change of the potential is maximum. We have several types of potentiometric titration like acid base titration, complexometric titrations, oxidation reduction titrations, precipitation titrations. Let us now come to acid base titrations. A known volume of the acid to be titrated with the base, and the EMF is measured after the each addition of base. The values of the EMF are then plotted against the ml of the base added. Now, if we look at the plot between EMF and the volume added, we get a S-shaped curve, and the end point is the point at which there is a sharp increase in the EMF. If we plot dEP by dV against ml, we get a very sharp change at the end point, and we can get the end point from this curve also. The E, that is the potential, is given by E naught plus 0.059 log activity of hydrogen ions. Then let us come to complexometric titrations. Complexometric titration can be followed with an electrode of the metal whose ion is involved in the complex formation. For example, a silver electrode may be used to the titration of cyanidine with a standard solution of silver. Ag plus when reacts with 2Cn minus gives AgCN2 minus, and the potential in this case is E is equal to E0 plus 0.059 by N log Mn plus, that is metal having N positive charge. Next is oxidation reduction titrations. In this case, oxidation reduction reactions involve the transfer of an electron or hydrogen atom or hydride group from a donor to an acceptor. The donor loses an electron and changes from the reduced to the oxidized form. The acceptor gains an electron and changes from the oxidized to the reduced form. The oxidized and reduced form of a redox component are said to form a redox couple. A redox titration is based on an oxidation reduction reaction between the analyte and the titrant. A potentiometric titration involves measurement of the potential of a suitable indicator electrode as a function of titration volume. For example, consider the titration of iron 2 with standard cerium 4 monitored potentiometrically with platinum and calomel electrode. In this case, we can write E is equal to E naught plus 0.059 by N log oxidized and divided by reduced. Then comes precipitation titration. In precipitation titration, insoluble salts of metals such as mercury, silver, lead and copper may be followed potentiometrically. The indicator electrode may be made of the metal involved in the reaction, a silver electrode for the titration of halides for instance, or maybe an electrode whose potential is governed by the concentration of the anion being precipitated. The magnitude of the potential change at the end point depends on the solubility of the substance being precipitated as well as the concentration involved. Silver electrode is normally used as cathode in precipitation titrations. Saturated calomel electrode is used as an anode and the potential can be represented as E is equal to E 0 plus 0.059 log x minus. Advantages of potentiometric titrations are they can be used for colored solution, whereas in normal titrations the colored solution causes problem because the end point is not clear. It is easy to interpret titration curves. The method is applicable for dilute solutions also. Several components can be titrated in the same solution without the possibility of indicators interfering with each other. For instance, bromide and iodide may be titrated together. To summarize, in this lecture we have talked about potentiometry, Nernst equation, types of potentiometric titrations, glass electrode, calomel electrode, silver chloride electrode, advantages of potentiometry, and we have also discussed various types of potentiometric